Our planet faces an unprecedented challenge, climate change, driven largely by increasing atmospheric carbon dioxide. For decades, CO2 has been viewed primarily as a waste product, a byproduct of industrial progress. However, a transformative approach is emerging, one that seeks to redefine our relationship with this ubiquitous gas. This approach is known as carbon capture and utilization, or CCU. At its core, CCU involves capturing carbon dioxide emissions from various sources and then transforming them into valuable products. It represents a paradigm shift from simply storing CO2 to actively repurposing it. The primary objective of CCU is clear: to mitigate climate change by reducing the concentration of CO2 in our atmosphere. This is a critical step in achieving global sustainability goals. CCU offers a dual benefit that makes it particularly compelling. Firstly, it directly contributes to reducing atmospheric CO2 levels, addressing the root cause of global warming. Secondly, it creates significant economic opportunities by repurposing what was once considered a harmful waste product. This innovative strategy turns a liability into a resource, fostering new industries and revenue streams. The journey of carbon utilization begins with effective carbon capture. Industrial facilities are the primary sources of concentrated CO2 emissions. These include power plants, cement factories, steel mills, and chemical production sites. Capturing CO2 directly from these large point sources is often the most efficient starting point. One widely studied method is post-combustion capture. This technique involves scrubbing CO2 from flue gases after the combustion process has occurred. The exhaust gases, containing CO2 along with other components, are passed through a chemical absorption system. Commonly, solvents like amines are used in this process. These chemicals selectively bind with CO2 molecules, separating them from the rest of the flue gas stream. Once captured, the CO2 is then released from the solvent, which can be regenerated and reused. Another significant approach is pre-combustion capture. Unlike post-combustion, this method removes CO2 before the fuel is burned. This is typically achieved by converting the fuel, such as coal or natural gas, into a synthesis gas. This synthesis gas is rich in hydrogen and carbon monoxide. A subsequent reaction, known as the water-gas shift reaction, converts the carbon monoxide into additional hydrogen and CO2. The CO2 can then be separated from the hydrogen-rich gas stream, which is then used as a clean fuel. A third advanced capture technology is oxy-fuel combustion. In this method, fuel is burned in an atmosphere of pure oxygen, rather than air. This eliminates nitrogen from the combustion process. The result is a flue gas stream composed almost entirely of CO2 and water vapor. This highly concentrated CO2 stream is much easier and more energy efficient to capture and purify. It simplifies the subsequent utilization or storage steps. Once captured, CO2 can be put to various uses, transforming it from a pollutant into a valuable commodity. One of the earliest and most established utilization methods is enhanced oil recovery, or ER. This application involves injecting CO2 into aging oil reservoirs. The injected CO2 reduces the viscosity of the remaining oil, making it flow more easily towards production wells. This process significantly increases the amount of oil that can be extracted from a reservoir. While effective for oil production, it's important to note that ER only offers temporary CO2 storage. A portion of the injected CO2 remains underground, but some may eventually return to the atmosphere. Beyond ER, CO2 can serve as a crucial feedstock for chemical conversion. This involves using CO2 as a raw material to synthesize a wide range of industrial chemicals. This approach directly integrates CO2 into the chemical manufacturing value chain. Products derived from CO2 through chemical conversion include methanol, a versatile chemical used in fuels and plastics. Urea, a key component in fertilizers, can also be synthesized from CO2. Furthermore, CO2 can be incorporated into the production of various polymers, which are the building blocks of many plastics and materials. Electrocatalysis represents a cutting-edge method for CO2 utilization. This mechanism employs electricity to drive chemical reactions that convert CO2 into more complex and valuable compounds. It often involves specialized catalysts that facilitate these transformations at lower energy inputs. Through electrocatalysis, CO2 can be converted into products like ethylene, a fundamental chemical used in the production of plastics. Other potential products include carbon monoxide, formic acid, and various alcohols, all with significant industrial applications. This method holds promise for using renewable electricity to power CO2 conversion. Bioconversion offers another innovative pathway for CO2 utilization, leveraging the power of biological systems. This mechanism employs microorganisms, such as algae and certain bacteria, to consume CO2 as part of their metabolic processes. These organisms effectively act as tiny biological factories. As they grow, these microorganisms convert CO2 into a variety of valuable products. These include biofuels, which can serve as sustainable alternatives to fossil fuels. Bioplastics, derived from biological sources, also represent a significant product. Additionally, bioconversion can yield other valuable compounds like proteins, pigments, and specialty chemicals, creating a diverse range of bio-based products. Finally, mineralization provides a long-term and highly stable solution for CO2 utilization and storage. This mechanism involves reacting CO2 with naturally occurring minerals, typically those rich in calcium or magnesium. The reaction forms stable carbonate minerals, such as calcium carbonate, which is essentially limestone. This process effectively locks away CO2 in a solid, inert form, offering a permanent storage solution. Mineralization can also be applied to industrial waste materials, such as concrete or mining tailings. By reacting CO2 with these materials, it not only sequesters carbon but also potentially enhances the properties of the waste, turning it into a useful building material. The potential benefits of carbon capture and utilization are profound and far-reaching. Firstly, CCU offers a critical pathway for reducing emissions from existing industrial infrastructure. Many heavy industries, like cement and steel production, are difficult to decarbonize entirely through renewable energy alone. CCU provides a vital tool to address their process emissions. Secondly, CCU has the potential to create entirely new industries and value chains. By transforming CO2 from a waste product into a raw material, it opens up opportunities for innovation, investment, and job creation. This fosters economic growth alongside environmental stewardship. Thirdly, the generation of valuable products from CO2 adds an economic incentive to emission reduction efforts. This can help offset the costs of capture and conversion, making CCU a more attractive and sustainable solution. It shifts the perception of CO2 from a burden to an asset. Despite its immense promise, CCU faces several significant challenges that require ongoing research and development. One major hurdle is the high cost of current capture technologies. The energy required to separate CO2 from flue gases and the capital investment for equipment can be substantial. Government incentives are playing a crucial role in accelerating the development and deployment of CCU technologies. Policies such as carbon pricing, tax credits, and research grants are encouraging investment and innovation in the sector. These incentives help bridge the economic gap for nascent technologies. Furthermore, accelerating research and development efforts are continuously pushing the boundaries of what is possible. Scientists and engineers worldwide are working to improve efficiency, reduce costs, and discover new applications for captured CO2. This collaborative effort is essential for overcoming current limitations. Looking ahead, CCU is poised to play a vital role in the transition to a low-carbon economy. It offers a pragmatic solution for industries that cannot fully electrify or switch to renewable fuels immediately. It complements other decarbonization strategies, rather than replacing them. Ultimately, CCU holds the potential to transform a major pollutant into a valuable resource. By closing the carbon loop, it moves us closer to a circular economy where waste is minimized and resources are maximized. This innovative approach contributes significantly to a more sustainable future for all.